Hello everybody, welcome back. Today we're gonna do some exercises in estimating pipe pressure drop. So in the last video we already discussed how through dimensional analysis we actually derive an expression for our K based on the Fanning's friction factor, and that can be derived from this graph. And it's just to give us a flavor of how these calculations are done, because these are experimental data charted over many experiments over various settings, so it can allow us to estimate pressure drop. And just a warning for you, you may find other graphs like the Moody chart. There's a Moody diagram that looks very similar to this, but on the y-axis, the vertical axis, the friction factor plotted is called the Darcy friction factor, and it's 4 times greater in magnitude than this Fanning's friction factor. Otherwise, it's pretty much the same. You just use that factor of 4 to convert between Darcy and Fanning friction factor. So not a problem. Okay, so anyway, we'll continue. So we'll just have a hypothetical case. Let's have oil flowing in a glass pipe. So this oil is called Dowtherm A. The properties are as follows. So okay, paste and go. Yeah, so these are the properties. You can see the vapor pressure, the viscosity, density, etc. So let's just take a look. We'll have room temperature Dowtherm A flowing along a 50-meter long pipe, which is 2 cm in diameter. We'll have two cases, 3 cm per second flow rate, 1 meter per second flow rate. And then we asked ourselves, what is the pressure drop? Now, why are we having these two flow rates? Well, if you see the Darcy friction, the Fanning friction factor graph, you'll see that there are actually two regions of the graph. So the left side actually represents laminar flow, where the flow is slow and, well, the viscous forces are significant enough so that the flow profile is pretty under control. Then you have a chaotic flow regime, or the turbulent flow regime, to the right, and you see these many lines down here. So the methods of calculation are slightly different, so hopefully we want to go through both of them in this video, and hopefully it is a short enough kind of a video. Okay, so first thing first, given this data, let's calculate a Reynolds number. So remember, Reynolds number equals to rho u d over mu. So let's do the first case. We'll need the density and viscosity. Okay, you can also write it like this, rho u d over nu. This nu, nu, that is this is the kinematic viscosity. Oopsie. It is just the ratio of mu over rho. So let's calculate that for this case. So what is mu? Mu here is, well, we don't have 30 degrees data, so I'm just going to take, we can extrapolate it, but I don't want to extrapolate it. Alright, so we're just going to take the about 1.6 millipascal per second, 1.6 times 10 to the minus 3 MPa second. And let's look at the density. Density, we'll just give it 1080. Here, can you see? 1080. That's just an estimate. Of course, if you have 30 degrees C data, that would be awesome, but I'm just giving it an estimate. Okay, this is just an estimate. It's not the fully 100% accurate way, but it's an estimate, just to give us an idea of how much pressure drop we typically can expect. Okay, so let's look at the kinematic viscosity mu. Alright, I'm just going to open Excel here to do some, well, calculation. I'm going to delete these old calculations and, well, let's do mu rho nu. Okay, what's mu? 1.6 e minus 3. What's rho? 1080 kg per meter cube, Pascal seconds. So the nu here will be this divided by this. Oopsie, other way around. This divided by this. 1.48 times 10 to the minus 6. Of course, we can increase the number of decimal places. So it's 1.4815. 1.4815 e all times 10 to the minus 6. So I'm a bit lazy to write out the SI units here. And I think this should be a Pascal second. Alright. Okay, so let's calculate Reynolds number again. For the first case, U times D. What's U? U is 0.03 meters per second times, what's D? D is a 2 cm, so 0.02 meter over 1.4815 times 10 to the minus 6. Alright. Reynolds number for the first case, 0.02 times 0.03 divided by this number. And what's this number? General format, 405, 405. Is this laminar or turbulent? Let's take a look. Yeah. Normally below 2300, that's a laminar flow. So if you look at this diagram, they tell you this F equals to 16 over the Reynolds number. Okay, that means it's pretty easy. You can either read it off the graph or you just use this F equals 16 over the Reynolds number. How they get this formula? It's actually through the, there is some calculus involved through something called the Navier-Stokes or Navier-Stokes equation, but we won't be discussing that just yet. So let's just take it as that. Okay, F equals to 16 divided by Reynolds number. So 16 divided by 405. Alright. Equals to 16 divided by the Reynolds number. So 0.0395. It's very simple. Okay. So let's calculate our K. Our K is as such. So 4 times L. L is what? 50 meters long. 50 meters long times 0.0395. That's F divided by, what's D? D is just our diameter, which is 0.02 meter. Right? So let's calculate our K. F times 4 times L divided by D, 0.02. 395. 395. I'll just leave it as 3 significant figure. Just not that. I'll just leave it. A bit lazy. Okay. So let's calculate our pressure drop given this formula. Okay. So this is just K times half rho V square. K times half rho V square. Okay, what's our V? Again, so a pressure loss. Okay, so K times 0.5 times, what's the rho? Rho is here, 1080. What's V squared? V is, in the first case, 3 cm per second, so 0.03 squared. 192 Pascal. Okay, so laminar flow is pretty simple. You just go through this procedure and you'll find your friction factor. Now let's consider the case. We consider the case of we consider the case of a faster flow rate. Well, now 1 meter per second flow rate. Let's consider 1 meter per second flow rate. Okay, this one I can go to next time. 1 meter per second flow rate. Okay. Alright, so my new is going to be the same, and the Reynolds number is just 1 meter per second times 0.02 divide by nu. And what's the Reynolds number now? Reynolds number is way above 2300, so this is definitely a turbulent flow situation. Okay, so Reynolds number, I'm not going to type everything down, 135. Okay, 1350. Okay, so just gonna copy this down. So U and D. So 1 meter per second times 0.02. So 2 cm diameter pipe. I'll copy this down here. Okay, so this is turbulent. Okay, turbulent flow. What do you do with turbulent flow? Turbulent flow is, well, you just adopt a slightly different method. So where's the Reynolds number? It'll be somewhere here. You can see 1 times 10 to the 4th. Okay, 1 times 10 to the 4th at the bottom. I'm clicking around here. 1 times 10 to the 4th, and this is 1.3 times 10 to the 4th. So that is somewhere on this line just before it actually on that line, somewhere on that line. Okay, I'm just gonna copy and paste and put it in pins because it's easier to zoom in. Okay, so let's zoom in. Okay, somewhere here, I'm not very sure, it's just a rough estimate, but immediately you'll see that this line actually intersects a lot of other small lines, right? Regardless where you draw the line. So the turbulent regime is slightly different. What is actually different? Well, you have to see what these lines are talking about. Now, if you scroll to the, just a little bit to the right, you can see these numbers here. Yeah, this one. This is for something called surface roughness to diameter ratio. What is surface roughness? Well, as we know, not all materials are created equal. Some materials resist flow more than others, and this resistance is characterized by something called surface roughness. So, what is the material of our pipe? We have a glass pipe. So for glass pipe, where can we look? Well, immediately in this table 6.1 from Paragus Chemical Engineering Handbook, we have some materials and their characteristic surface roughness. So remember, these units, they are in millimeters. You can see millimeters, and we're going to look for glass pipes. So glass pipes are here in the drawn tubing category. The surface roughness is 0.00152 millimeter. So epsilon equals to 0.00152 times 10 to the minus 3 meter. So we want to look for epsilon by d. So we'll just divide by d. Right. So what's d? D is again 0.02 meter. Okay, so we'll need to calculate this ratio first. E divided by d. Okay. 0.00152 times 10 to the minus 3. 0.00152 E minus 3 divided by 0.02. So this is the number we get, 0.0000, that's 4 zeros there, 4076. So where do we look? Look back at our diagram, which should be on pinned. So we look for 4 zeros here, 0.000076. Now where would that be? You can see it's just in between these two numbers, okay, somewhere in the middle there. Okay, so we'll just follow where this line is actually going. Okay, and then as you realize, the line actually kind of disappears over here, but it means that we can just consider it as a smooth tube eventually. So this is our friction factor, thereabout. Okay, friction factor, you give and take 0.0072 or 73. I didn't draw my lines very straight, but that's how we find our friction factor, 0.072. And then we'll calculate our K using the same formula. So for FL over D, okay, for FL over D, and let's calculate the pressure loss. Okay, so that just for presentation's sake, I'll do a very quick one. This is 0.0000 something 76. So here is 0.00072. Alright, that's the F value, fanning friction factor. Let's calculate our K, which is 72. And now we can just look at our pressure drop. So this is 72 times 0.5 times rho, which is 1080, times V square. Conveniently, is just 1. Okay, let's calculate the pressure drop. Okay, so this is going to be here, and we're going to use 1. Alright, can you see the pressure drop is a lot bigger? 38880 Pascal, or 38.88 kilopascal. So that's how we find that, okay, for turbulent flow we'll have more pressure loss. Okay, hope this video was helpful in helping you learn to use this Moody chart and for both laminar and turbulent flow. So we'll see you again. Thank you very much for watching. Bye bye.